Hey guys, welcome back to chapter 18. What we're going to take a look at now is a different way to calculate Gibbs free energy, or delta G. As you remember, for entropy, we had a table of standards, so experimentally determined values for substances that are at standard state, 1 atm, room temperature. Well, we have the same kind of calculations for these Gibbs free energy, so we can use these standards to also calculate Gibbs free energy. So just another option of calculating it. So standard free and the energy of formation is the change in free energy when 1 mole of a compound forms from its constituent elements in their standard states. So as these molecules come together, energy is released. And the energy that is released is the standard Gibbs free energy. This formula should look very similar to the one we used for S, way more confusing than it needs to be. So we'll break it down. So to calculate the standard free energy of formation, we're going to take the products minus the reactants. So that's really what this whole big long thing is saying. So products minus reactants. And remember this value right here, this E is telling us that we're going to sum all of the products together, and then we're going to sum all of the reactants together, and we're going to subtract those two sums. And then this guy, remember, is just saying, well, you have to take into account how many moles of each is being made. So this just addresses the stoichiometric coefficients. Looks like a messy formula, but it's actually really easy to use. So that's exactly what we're going to do. We're just going to dive right into a problem. So I want you guys, or what we're going to do together is calculate the standard free energy of formation for the following reaction. So here's our reaction. Here's our table of standards. And we want to calculate what is the Gibbs free energy for the entire reaction. Okay. All right. So the formula that we're ultimately going to use is the standard free energy for the reaction is going to be the free energy change for the products minus the free energy for the reactants. Okay. So I always like to do products first, just because that's the first one that comes in our equation. So I see that this has 3 products, so I'm going to have to add all 3 of those together. So the first one is carbon dioxide. So I see carbon dioxide is negative 394.4. Oops. So negative 394.4. Let's take a peek at the units here. So the units are kilojoules per mole. So kilojoule is a unit of energy, and then per mole tells us that we have to take into account how many moles are being made. So this is kilojoules per mole, and there's 1 mole in our reaction. Okay. All right, so the next one is water in the gas form. Remember, if you're looking at a big table, you do need to keep an eye on the state. So the next one is water. So water is negative 228.6 kilojoules per mole. And in our reaction, we are making 2 moles of water. And then, oopsies, our last product is this O3. So O3 has a Gibbs free energy of positive 163.2. kilojoules per mole. And we are making 4 moles of that. Okay. All right, so let's plug this into our calculator for each of these moles. Moles is going to cancel. So I've got negative 394.4 times 1 is negative 394.4 kilojoules. Negative 228.6 times 2 gives me negative 457.2 kilojoules. And positive 163.2 times 4 gives me 652.8 kilojoules. And then I add all of these together, keeping a close eye on my negatives here. So negative 394.4 plus 94.4 plus negative 457.2 plus 652.8. And for the products, we get a change of 198.8 kilojoules. Okay. Now I'm going to do the same thing for the reactants. All right, so reactants, we've got 2 reactants here. The first one is CH4. Whoops, I don't care that it's CH4. I want the number. So the first one is CH4, that's negative 50.5 kilojoules per mole. And we're making 1 mole. Oops. And the other one is O2. So remember that the definition here was the change in free energy when 1 mole of a compound forms from its constituent elements. Well, we see that oxygen has a 0 for the Gibbs free energy standard. That's because it is its elemental form, right? Oxygen doesn't exist as just oxygen by itself. It exists as O2. So O2 is the elemental form. So the Gibbs free energy for that is 0. And just for completeness sake, we're making 8 moles of that. So moles and moles cancel. We've got negative 50.5. We've got 0. So the reactants is negative 50.5 kilojoules. Okay. So the last thing here is just to plug these into our equation. So products minus reactants. So our products is negative 198.8 kilojoules minus our reactants, which is negative 50.5 kilojoules. Again, paying close attention to our negatives here. So negative 198.8 minus negative 50.5. And we get that the Gibbs free energy for this reaction is negative 148.3 kilojoules. Okay. So just another way to calculate Gibbs free energy, and we're doing this from standards. I hope you guys found this helpful.